Hey everyone, in Chemistry 40 land, this is Dr. Carroll here. We are looking at Unit 2, Lecture 4 in our course. This is on page 15 in your Unit 2 booklet, and this is all about the polarity of molecules. We've looked at bond dipoles, mu bond, but what about a molecule itself? Can it have a positive and negative end? The answer is yes, and Vesper helps us determine if it does. Why do we care? Well, in a capacitor, which is an electronic component that stores memory and energy, you have one in your calculator, in your VCR, remember those, in your computers, all sorts of capacitors. The filling of the capacitor is important in how much memory can be stored, and depending on the polarity, you can get more memory, less memory. Polar molecules are important in nerve impulse transfers in your body. So biochemistry is another reason, and I'm sure you can research all sorts of other reasons for you to know why a molecule is polar or not. So this is Unit 2, Lecture 4 on bottom page 15. If a molecule, I'm focusing on covalent molecules here, has the bond dipoles not vectorially canceling out, then it is a polar molecule. Otherwise, it's not. So let's go here. And in the handwritten part, polarity of molecules continued. If a molecule is polar, it has a permanent separation of charge. The molecular dipole mu molecule is greater than 0. So mu molecule is the vector sum of mu bond. Hopefully you took Physics 30S and know a bit about vectors. So we add vectors together, and if they do not cancel to 0, then you have a polar molecule. If they do cancel to 0, you have a nonpolar molecule. So, well, here it is again. If the molecule is polar, the bond dipoles do not cancel out completely. If the molecule is nonpolar, the bond dipoles do cancel out completely. If you have molecules with polar covalent bonds, they may or not be polar. You have to look at what the ligand types are and what the molecular geometry is. So let's just survey through, and we'll start with something you don't even need to know Vesper for this. Homonuclear, the same kind of nuclei, diatomic molecules are nonpolar. So oxygen is a nonpolar molecule. It doesn't have a positive and negative end. Nitrogen is nonpolar. It doesn't have a positive and negative end. Heteronuclear diatomic molecules, all of them are polar. Okay, hetero meaning different. So you have hydrogen and fluorine and hydrogen fluoride. The hydrogen is a partial positive end, fluorine partial negative. So the mu bond is directed towards the fluorine, but that's the only bond there is. So the mu molecule is the same as the mu bond. So this is a polar molecule, and it would line up with other HFs, and you could get hydrogen bonding. Hydrogen bonding, another reason that we need to know polarity of molecules. If you have a linear triatomic molecule, they're nonpolar if and only if, in math we go IFF, that means if and only if the ligands are of the same type. So in carbon dioxide, oxygen is more electronegative than carbon, so you have a mu bond to the left, but you have the same value mu bond to the right. So it's like taking 3 steps to the left, 3 steps to the right, you end up in the same place you started with. So it is a nonpolar molecule. If we replace an oxygen with a sulfur, then it becomes a polar molecule because one arrow isn't, I mean, if sulfur is a little bit more electronegative than carbon, let's say, but oxygen is a lot more electronegative than carbon, so the oxygen end will be your partial negative end of that molecule. So that would be a polar molecule. If I went back to carbon disulfide, well, that's going to be nonpolar. Carbon disulfide would be nonpolar. Bent triatomic molecules, they're all polar. Anything that has a molecular geometry that is bent, however it's bent off of, it is going to be a polar molecule. So oxygen difluoride is a polar molecule because you have the 2 bond dipoles, so they add together, so you have this big push down, but you don't have any ligand above to cancel that out. So oxygen difluoride is polar. Water is polar. Ozone is polar. So anything that has a bent molecular geometry is a polar molecule. Same with pyramidal. Fifth one, pyramidal molecules, they are all polar as well, because here you have a nitrogen trifluoride. So you have 3 bond dipoles pushing down, and you don't have an atom up, so your negative end is at the midpoint between those 3 fluorines, and positive end near the nitrogen. So anything which has a pyramidal molecular geometry, that is a polar molecule. Trigonal planar, a bit more involved. They are nonpolar, but only if the ligands are the same type. If the ligands are of different type, then they're going to be polar. So for example, in BF3, so you have like a pull up and pull this way and a pull this way. It's like 3 people moving a piano on casters, and they all have the same strength, and they're all 120 degrees from each other, and they all pull at the same time. The piano doesn't go anywhere. So that's what we're saying here. The bond dipoles cancel out completely in BF3, so even though there are 3 polar covalent bonds, the molecule itself is nonpolar. If you want to do it in terms of resolving vectors, you can think of like this and like this. So you resolve vectors into horizontal and vertical, so the horizontals cancel, the verticals add up, but they cancel out the vertical going to the top, so the whole thing is nonpolar. Okay, but if we have one atom different than the other 2, then it becomes polar because your strengths aren't the same amounts. Tetrahedral molecules, they're only nonpolar if all ligands are the same type. If they're different, even one different than the others, then it's polar. So methane, for example, is nonpolar, but what is this one here? Why do I have it polar here? Why do I have C's there? I shouldn't have C's there. Let's make these H's. H, H, H. So one of the H's is replaced by chlorine. That's now polar. If I look at something like carbon tetrafluoride, there all ligands are the same. The fluorine is more electronegative than carbon, but this is nonpolar because the poles are going to cancel each other out. And if you have a molecular model kit with you, you can see that they cancel each other out. Sometimes I draw it like this to talk about molecular aerobics. So I have, it's like to the right and up, to the left and up. So the rights and lefts cancel, the ups double up. And towards you and down, towards me and down. So the downs double down and cancel with the double ups, and the U's and me's cancel, so the whole darn thing is nonpolar. But if I change just one fluorine to something else, then it becomes polar. For the honor kids only, you can look at trigonal bipyramid. They're nonpolar if all the sections are of the same type. But if the sections are different, the equatorial and the axial, then they're polar. Seesaw molecular geometries are polar. T-shaped molecular geometries are polar. Octahedral are nonpolar, again, only if the sections are the same type. Square pyramids are polar. And don't worry about the textbook. That was a different textbook. Anyways, that was just for the honor stuff. So you can try on bottom of 17, decide whether those are polar or nonpolar systems. And then we see in worksheet Belmont here, you want to draw the Lewis structure, determine the electron group geometry, molecular geometry, bond angles, and the polarities for them. So shall we try one here? PS3 minus. What the heck is that one? And it's a -1. Let's omit that one. I don't like that one for a few reasons. CF2S. Let's try that one. Okay, so the fluorines are bonded to the carbon. You memorize that. This is a derivation of formaldehyde, really. So the egg is trigonal planar. The molecular geometry is trigonal planar. This is a polar molecule because not all the ligands are the same. So this is a polar molecule. SHF. I guess the fluorine and hydrogen like to be terminal. So this is going to be, this is the Lewis diagram. The electron group geometry is tetrahedral. The molecular geometry is bent. This is a polar molecule. Okay, BH3 is a nonpolar molecule. SF2 is a polar molecule. P2H4, let's not worry about that one with the two centers. Some more practice on writing some Lewis diagrams. Copy out a big VSEPR table that you can find. That's just good practice to get you organized, including whether something is polar or not. Here's some more stuff with worksheet Belmont. Playing the VSEPR game, getting the polarity for various examples. Okay, good practice, Belmont, that's for sure. Draw your own examples of various electron group geometry, molecular geometry. Don't use examples, use fresh examples. Okay, that sounds good. Worksheet Pinto is yet more practice. Some of these you've seen before, so it's just extra practice. That's good as we finish up the chapter. Okay, good. And now where are we going to go here? Naming. You should get a bit of practice with naming. Here we have some naming examples on page 25. And then the reverse. Crimson worksheets, more practice to try out. Okay, to become a superstar at the whole Unit 2. And everything's all interrelated, for sure. Fun sheet rainbow is just matching things up, writing more examples, and get more examples of playing the VSEPR game and namings. Some of these namings you've seen before in a previous worksheet. Notice something familiar? So what? It's excellent practice. It sure is. There's more practice for naming. And polarity practice. Determine which is more polar. That's an interesting one. Like what's more polar between water and hydrogen sulfide? And water would be more polar because oxygen is more electronegative than hydrogen. And chloracetylene would be more polar because it's more electronegative than bromine. Okay, so that's a good question. Some Lewis structures, some more practice with VSEPR. Some students ask, they say, what if there's more than one central atom like there is in C2H2? So C2H2, you would just have two central atoms. So one central atom here, right? So you think of the whole rest as one group, and there's one group, so it's linear with that group. And then look at this carbon as a central atom, and think of this all as one group, and this is one group. So it's linear. So that works okay. 33 is more examples for VSEPR. Oh, I see some cis and trans. Don't worry about that. Dichloroethene. Then a quiz, which we'll talk about later. So I think that's it. Check my page down here. Quiz with lots of examples, lots of questions, and that's it. So that is it for our Unit 2. Now, start practicing it all. Have fun.